after seeing that last example where we had that line integral of the vector field f, where we saw this example where we looked at the line integral from a certain point 0, 0 to another point 1, 1, and all of the line integrals ended up being the same value, regardless of which path we picked. So what we're going to write down now is a summary of the reason that happened. So we're going to look at the fundamental theorem of line integrals. So first off, we're going to let C be some curve. It's a piecewise smooth curve lying in an open region R, and the curve C is given by R of t equals x of ti plus y of tj, where t runs from A to B. So then what we're going to take a look at is we're going to see if, say, capital F of xy, so this is going to be some vector field. Let's say that it has components m and n, which is kind of reminiscent to when we talked about these in the past. The condition that we're going to need for this fundamental theorem is we need this vector field to be conservative. So if this is conservative, which, remember, to be conservative means that it has a potential function. So let's say that it's with potential function, let's call it like a little f of xy, and that would be a function. So then remember what that means is that capital F equals the gradient of little f, so it's the partial derivative stored in a vector. Then what we're going to have for this theorem is that the line integral over C of f dr, which, remember, that really means f is this gradient of little f. So if you do take the line integral of a gradient, then the fundamental theorem says it's very similar to the regular fundamental theorem of calculus. So we're going to take that function f, we're going to take the potential function, and we're going to evaluate it at our further endpoint. So in the x component of this, so we're going to use the x component of r from up here, and then we're going to evaluate that at b. So we're going to do f of x of b, comma y of b, and then we're going to subtract off doing f of x of a, y of a. So also we can notice what we've done at that point is we have evaluated f. Instead of using x and y, we've plugged in the t values into that. And so we've been able to see essentially then what happens is this x of b, y of b would really be like the terminal point, right? That would be the point that you would get at the end of this curve C up top when you plug in b into r, whereas this second point when you plug in a is really the initial point. So one of the things that's really interesting then is we don't necessarily need to know what specific curve it was. It really just depends on the potential function, that little f function, and what were the initial point and terminal point of curve C. So this is where we get this idea of curve independence, where it ends up that it doesn't really matter what specific expression this r of t was, it just matters what was the initial point and what was the end point of it, which we might know in a different way regardless of the parameterization of that curve. So one of the things we can do then is kind of take a look at recreating that last example, but by using this fundamental theorem. So I'll leave that at the top of the page here. So in our previous example, the one that we started off with in the last video, we had the f, if we remember, was that vector field xi plus yj. And this was the one that we did from various points So we found the line integral along various curves from 0, 0 to 1, 1. We did like the straight line, y equals x, we did the square root function, we did the y equals x squared function, and we all got the same thing in each of them. So we're going to see if there's a different way to do it rather than actually parametrizing the curve and using that definition of this line integral. So one of the things we're going to need up top is we need to know what that potential function is. Let's first confirm f is conservative. So remember to check that. We're going to take the partial derivatives of our components. So this would really be like our m, and this would be our n. So the x component followed by the y component. Remember when we do the check, it's like we're looking to see if we have equal mixed partials. So we're going to take the partial derivative of m, which is the x component. We'll do that one with respect to y. So this is going to be the partial derivative with respect to y of x, which we can see is 0. And then we're also going to take the partial of n, and we'll do that one with respect to x. So this is going to be the partial with respect to x of y, which is also 0. So since these are equal, so since the partial of m with respect to x equals the partial of y with respect, the partial of m with respect to y, let me fix that, equals the partial of n, we're just writing all kinds of typos, that's okay. Since the partial of m with respect to y equals the partial of n with respect to x, f is conservative. So let's find the potential function. So we're looking for the function whose partial derivatives gave us those components of f. So that potential function, if it's little f, then it would have like the partial derivative with respect to x is that m component, which in this case is x. And we would have f sub y is y. So then let's say take a look at f sub x. Let's do the integral of f sub x, and we'll do it dx. So we'd have the integral of x dx. So x is going to go then to x squared over 2. And then remember, our constant is really a whole function. We're going to end up with a whole constant function. Let's just call it g of y. Anything that's in terms of solely y would have had a partial derivative where those terms would just go to 0 when we take the partial derivative with respect to x. And then let's do this one where let's just take the partial or the integral with respect to y as well, and then just compare and see if we can identify those constant functions. So this is going to be the integral of y dy, which is going to be y squared over 2 plus some function, let's say h of x entirely. So then by comparing these should be the same function. So f of xy equals either of those, x squared over 2 plus g of y, and it's also equal to y squared over 2 plus h of x. So we would then end up seeing that g of y is this y squared over 2, and h of x is this x squared over 2. So we're going to end up needing x squared over 2 plus y squared over 2, and then both of those h of x and g of y functions would technically have plus a scalar constant c. Now when we actually plug into our fundamental theorem up top, that scalar c is just going to cancel out anyway. So for this particular purpose, I don't need the plus c, but it is technically there. So then what we see up top, what we're going to end up doing is evaluating that line integral by simply evaluating this function at the initial point and terminal point. So I need to scroll a little bit here. But so then what we're going to end up with for our example is that the line integral of c of f dr is going to be, we'll take that potential function we just found, which was x squared over 2 plus y squared over 2, and we're going to evaluate from initial point, which was 0, 0, to the terminal point, which was 1, 1. So we're going to plug in 1, 1 first, same kind of pattern as before, right? Plug in like your b first and then followed by your a. So we'd have 1 squared over 2, which is a half, plus 1 squared over 2, which is another half. And then we would subtract off plugging in 0, 0, which is just going to give us 0. And you'll notice that we get 1, which is what we saw in all of the previous examples. So this saves us the steps of having to, know what curve C even is. Notice it didn't even matter what C was. All that mattered was the initial point and terminal point. So this is this concept of path independence. You can essentially, it doesn't matter which path we took. We were able to get to the same answer regardless. So not only did we not need to know what path it was, we also didn't need to parameterize it. So we'll take a look at a couple more examples in our next videos.